Now our next operation we're going to look at, well, actually our last one for today, is matrix multiplication. Matrix multiplication is a bit different from scalar multiplication. This is what we're doing when we're taking two matrices multiplied by each other. For the record, matrix division is not defined. You can't take a matrix divided by a matrix. So matrix multiplication, first, the first matrix, the first matrix's number of columns must match the second matrix's number of rows. So if you're taking A times B, then A has to have dimensions m by n. B then has to have n rows and then can have any number of columns. Then the result is a matrix. So the middle ones have to match the number of columns of the first matrix, the number of rows of the second matrix, and then the outer values, the number of rows of the first matrix, the number of columns of the second matrix, determine the dimensions of the result. So if, for example, we take a 2 by 3 times a 3 by 4, we can do that because these are both 3, but then the result would be a 2 by 4 matrix. Okay. So, for example, let's say we have matrix A, -1, 0, 4, 2, 1, 3. Matrix B is 2, 1, 4, -3, -6, 4. And then we'll say C is -1, 3, 2, 3, 1, 0, 0, -4, 5. Right. And we want to evaluate a few things. Let's evaluate A times C. Well, the way matrix multiplication works is you take the rows of the first matrix and multiply them down the columns of the second matrix. So let me write out these matrices. I've got -1, 0, 4, 2, 1, 3. That's matrix A. Matrix C is -1, 3, 2, 3, 1, 0, 0, -4, 5. Okay. First off, A, this is a 2 by 3 matrix, 2 rows, 3 columns. C has 3 rows, 3 columns. So we can multiply because those middle dimensions match. Our result is going to be a 2 by 3 matrix. Now, in order to find what goes in that 2 by 3 matrix, we take each row of the first matrix and go down each column. So first we match row 1 here to column 1 here, and we multiply each entry. We take -1 times -1. We take 0 times 3. We take 4 times 2. And we add those all together. The result of that is going to be the entry for row 1, column 1 of the answer. Then we go row 1, column 2. And we multiply each entry. -1 times 3 plus 0 times 1 plus 4 times 0. And that's taking row 1 times column 2. So that entry goes into row 1, column 2. And finally, row 1 times column 3 goes into row 1, column 3 of the new matrix. Take the first entry, -1 times 0, plus 0 times -4, plus 4 times 5. I didn't budget my space very well. Hopefully you can still see that. Yeah. And then we go row 2, column 1. So that's 2 times -1, plus 1 times 3, plus 3 times 2. Then row 2, column 2. It's going to be 2 times 3 plus 1 times 1 plus 3 times 0. And then row 2, column 3, we get 2 times 0 plus 1 times negative 4 plus 3 times 5. And then we just work out the arithmetic, and we've got our matrix there. 1 plus 0 plus 8 is 9, negative 3 plus 0 plus 0, 0 plus 0 plus 4 times 5 is 20. We have negative 2 plus 3 plus 6, which is 7. We have 6 plus 1 plus 0 is also 7. 0 plus negative 4 plus 15 is 11. So that's how we go about multiplying matrices. Say I wanted to evaluate C times A. Well, in that case, C is a 3 by 3, A is a 2 by 3. These two don't match, so this is not possible. Which illustrates something about matrix multiplication, that it is not commutative. With numbers, multiplication is commutative, meaning that the order of the multiplication doesn't matter. 3 times 4 is the same as 4 times 3. But matrix multiplication is not commutative. A times C, we got this. C times A, not only do we not get the same answer, but we can't even do it. So even if you can do the multiplication both ways, which is possible, that doesn't mean you won't get the same result in general. As just sort of an FYI, there's a special matrix called the identity matrix, and there are many different identity matrices. And the identity matrix is a square matrix with ones on the diagonal and zeros everywhere else. The reason there are many identity matrices is because there's a 2 by 2 identity matrix, there's a 3 by 3 identity matrix, there's a 4 by 4 identity matrix, and so on. So, for example, you always have 1, 0, 0, 1, 0, and you just keep having zeros all the way to the end, and then ones all the way down the diagonal. And I'm putting dot, 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 because it could be any number of dimensions, could be, but it does have to be square. The reason it's called the identity matrix is that any matrix times the identity matrix gets you that matrix back. So the identity matrix is like the matrix equivalent of the number 1. If you take any number times 1, you get the number back. So that's just sort of an introduction. That is what the identity matrix is. We'll do a little more with it in the next section. And one last thing, just with matrix operations, another way that we can represent a system of equations as matrix multiplication. That's another way we can represent a system of equations. For example, say we had the system 2x plus 3y minus c equals 7, negative x plus 2y plus 3z equals 6, 2x minus 2y plus 3z equals 1. Well, you can represent this as a matrix multiplication problem. You can represent it as AX equals B, where A is your coefficient matrix, X is your variable matrix, and B is your solution matrix, I guess. Yeah, so if we take this system and put it into this format, we can pull out the coefficients at 2, 3, -1, -1, 2, 3, 2, -2, 3. And then we're multiplying that by our variable matrix. We have 3 variables, so that we put that into a 3 by 1 matrix. We set that equal to our solution matrix, which are the answers from the right side, 7, 6, 1. Now you notice if we were to carry out this matrix multiplication, we'd take row 1 times column 1. So we'd get 2x plus 3y minus z, and that would be equal to row 1, column 1 here. 2x plus 3y minus z equals 7, which is exactly our first equation. We take second row times this, we get negative x plus 2y plus 3z equals 6. And in the third row times the column, we get 2x minus 2y plus 3z equals 1. So this is another way that we can represent a system of equations. We can represent it as matrix multiplication. And we'll do a little bit with that idea in section 3 as well. There are a couple questions on the homework for this section. Let's say to write it like this, then write the matrix as or write the system as an augmented matrix and solve using Gaussian elimination or something like that. So that's just, you write it like this, but then you would then go back and rewrite it as an augmented matrix like we did in section 1, like so, and go through the process of Gaussian elimination to solve, where you add rows and stuff. And that's just to get you more practice doing Gaussian elimination, because it's a long process and it's good to practice. That's really it for 8.2.